So next up is Ryza from Cloudera, and it's a pleasure to introduce him. I've actually worked with him. He actually implemented one of the schedulers that I wrote a paper about, one of the research papers, and it turned out that many of the things that we thought would work in theory actually do not work in practice. So he actually went through the pains of making it work.
Hello, everybody. So I'm going to be talking about Spark and resource management on Hadoop. The title of the talk is Can't We All Just Get Along? So my name is Sandy. I'm a software engineer at Cloudera. I work on MapReduce, Yarn, and some other resource management stuff that we do there. And I'm a committer on the Apache Hadoop project. So this talk is going to be about including Spark as a first-class processing framework on the Hadoop platform and on Cloudera's platform as well. So one of the key challenges here is resource management. And what I mean by that in this talk is we have a Hadoop cluster with some finite amount of resources, and we want Spark to coexist with other data processing frameworks that are citizens of the Hadoop cluster, and do this in a way that allows cluster administrators to prioritize and shape workloads in flexible ways. So I'm first going to talk about what we have already. I'm going to give some background on Yarn and on the Spark on Yarn work. And then I'm going to talk about what we need for the future to really make this system sing. So why do we have this problem in the first place? Why can't we just allocate one set of machines as a Spark cluster, and then one set of machines as a MapReduce cluster, one set of machines as an Impala cluster, and do our computation in these disparate places? So one of the main ideas of Hadoop is that we want to bring the computation to the data. So on the same data set, we might want to do ETL type of stuff with Pig and MapReduce. We might want to fit a machine learning model to it with Spark. And then we might want to have BI tools query it with Impala. Of course, this is just a tiny subset of tons of things that people might want to do with their data. And so we want to do all of this using the same set of machines so that Spark, Impala, MapReduce tasks can all go to the same places where the data is. So Hadoop brings generalized computation to big data. And it increasingly has more processing frameworks. It started out with MapReduce. At Cloudera, we use Impala pretty heavily. We've recently added SAS, and Spark now is one of the new and exciting things. So alongside of this, a cluster has a finite set of resources. There's a limited amount of CPU, there's a limited amount of memory, and there's a limited disk and network I/O. Some workloads are more important than others, and we don't necessarily mean to say that MapReduce is more important than Impala or Spark is more important than SAS. What we mean to say is that some very high priority reports might be very important, and independent of what framework we are computing those with, we want those to stand out above, let's say, exploratory data analysis kind of stuff. So our big question is, how do we make sure each workload gets the resources it deserves, and give administrators controls to enable what they need to do? So as a systems programmer, the way I'm inclined to see a system like this is, we have these processing frameworks that all sit next to each other, and then there is this big old storage file system underneath it. For an organization, though, the way they would really like to be able to see it is as a Hadoop cluster has some set of resources, and then those resources are subdivided between different departments and subdivisions of the organization. So what we'd really like to do is allow the subdivisions of this organization to use the tools that are the best for their job. They might want to use all of their resources on a MapReduce job at one point, and then 20 minutes later run some work that requires Spark or Impala. They might even have pipelines that they run regularly that combine all three. So how do we achieve this? The approach that Hadoop has taken has been to insert central resource management and layer these underneath the data processing applications. In Hadoop, this layer is called Yarn, and it's responsible for deciding what gets to run work on a Hadoop cluster and when it gets to run that work. So before we go into Spark on Yarn, we're just going to talk a little bit about Yarn its terminology, how it works, and what it can and cannot do. So Yarn is a resource manager and central scheduler for Hadoop. Central to the Yarn terminology is this notion of a container. And a container is a process scheduled on the cluster somewhere with some resource allocation. Currently, Yarn tracks memory and cores for CPU. Each container belongs to an application. And an application comes from a framework like MapReduce, Spark, or Impala. There's not a single application per framework. At least in these cases, think of it as an instance of a program running on your machine versus that program, like a Vim process versus Vim. So application masters. This got a little messed up when I moved it to LibreOffice. Each Yarn application has an associated application master, which is a process that is responsible for requesting resources from Yarn. So an application master comes up at the beginning of when the application is running, lives for as long as the application needs to request more stuff, and finally, when the application is completed, goes away. An important thing to know when designing Yarn applications is that applications startup time is non-negligible. It's usually on the order of a few seconds. So, if we want to be able to run work very quickly, schedule tasks very quickly, we have to have our application started and pre-warmed up before we do this. Once an application is started, acquiring resources can happen very quickly. So here's my rendering of the Yarn architecture. We have this single resource manager daemon, which is the central scheduler responsible for managing all the resources on the cluster. And then on each of the nodes in the cluster, we have a node manager. And the node manager is responsible for launching work on that node, as well as for enforcing resource limits. So it'll kill a process if it goes over memory. It'll set up C groups so that processes can't use more CPU than they were allocated. And you can see that in most cases, the application master itself runs as inside a container on the cluster. In the MapReduce case, it'll then go back and request containers that it can run map and reduce tasks in. Lastly, with Yarn, Yarn has this notion of queues. And queues are the way that we divide up resources within a cluster and give them to different organizations or individuals. So each application belongs to a queue. And we have a few different schedulers that will enforce various policies on these queues, but the basic idea is that between queues we want to share resources fairly, and we can tweak weights. Queues are hierarchical; they can contain subqueues. So for a larger division and organization, you might allocate 50% of the resources, and then within there you might allocate to smaller groups or even individuals. There are a few different application models that predominate on Yarn. The most simple application model is the one used by MapReduce. And this is where we have an application master or an application per job. At the beginning of the job, we fire up an application master. It requests the resources that are needed for the job. The work is done, the job completes, the application master goes away. This is very simple. It's the one used on MapReduce. The disadvantage of this is startup time. Latency is not extremely good, so if you want to be able to run things very quickly, this can be a while. Application master per session. This was recently added in TES. And the idea is that you start up an application master, and then you run jobs within it. So you still incur the costs of requesting containers once your application master is up. You don't have to start this application each time you want to run a job. Last of all is the application master as a permanent service. It's always on, and it waits around for jobs to come in. And this is sort of similar to the way we do things for Impala. It's a little more complicated, but we'll talk about that later. So Spark usage modes, and we'll talk about how we can map these in a second. Spark is used in a few different ways. First, it's often used for batch computations in the same way that MapReduce is. You want to ETL or transform some data, and interactive latency is not that important. So in this case, we use applications in the same way that MapReduce does. Our application master is not long-lived, and we only want to build a job to a single user. Spark also supports interactive usage, where someone fires up a Spark shell and then it wants to be able to explore data interactively and get back results very quickly. In this case, we have demands for this sort of like long-lived sessionized idea, but it's still a single user. Last of all, there's the server model, where a single Spark context or a single Spark application is running work on behalf of many different people. And this is used, for example, in the Shark server case. And so here it's both long-lived and supports multiple users. So Spark on Yarn. What do we have towards this currently? A lot, in fact. People at Yahoo, Tom Graves over there, have been working on a Spark application master that allows running Spark jobs on a Yarn cluster. So a Spark executor is a process on the cluster that runs tasks, and I'm pretty sure the way it works is there's a single container per Spark executor, and you have an application around for, I believe, a single job. So it's currently useful for Spark batch jobs. It requests all the resources that it needs up front. So you say, I want processes on 20 worker nodes, and I want each of those processes to have this amount of memory and this amount of CPU. So enhancing Spark on Yarn. While what we currently have works well for the batch use case, it still has some issues for the long-lived and interactive use cases. So we want to be able to support long-lived sessions with multiple jobs, and we want to perhaps be able to support multiple users. So more specifically, what are our goals towards this? Well, what we'd really like to be able to do is hang on to few resources when we're not running work. So if I instantiate a Spark shell, I shouldn't necessarily have to know how much memory I'm going to use. And while I'm sitting there thinking about what I want to type, I shouldn't be preventing other people in my organization from having access to those resources. What would also be really nice would be to be able to use lots of the cluster when it's not being used by others. So if my allocation is only 20% of the cluster, but it's 2 in the morning, no one else is using the cluster, it would be really good if I could use the entire cluster. And sort of a corollary to this is we want to be able to give back resources gracefully when we're preempted. So when someone comes, wakes up in 3 in the morning, decides that they have to run their really important job, I should be able to give them back resources without actually killing my job. And then last of all is sort of a performance requirement. We want to be able to get resources quickly when we need them to support interactive use cases and fast kind of stuff. So Spark currently has something like this for Mesos, not for Yarn. And the way that it works is it allocates static chunks of memory at the application's startup time, but it doesn't allocate any CPU. And CPU is only requested from the central scheduler when, when tasks are running. So how can we do this in Yarn? We can use most of the existing Spark on Yarn work that we have. A Yarn application master per Spark application or Spark context still holds. One executor per application per node, and one Yarn container per executor. And then the next step is allowing executors to acquire and give back resources dynamically. So in terms of on the Yarn side, what do we have to do to achieve this goal? First of all, long-lived Yarn is Yarn was originally built with frameworks like MapReduce in mind. So for example, it has these fossils like an idea of progress for an application. If you have like an interactive session, there's no idea of progress up to 100% because who knows when you're done. There's a lot of other miscellaneous work that has to do with what happens when things are restarted. Do you lose all your work? Can you renew your security tokens and leases in that way? So there's that stuff. Second of all is resizable containers. So currently, whenever you start a process on a Yarn cluster, that process has a fixed amount of memory and a fixed amount of CPU. For this to even work, on the level of the Mesos fine-grained mode, we need some way to allow you to increase and decrease the allocation of a running container on Yarn. So both of these are currently being worked on. Yarn 896 has a bunch of sub-zeros that are slowly being knocked off, and Yarn 1197 has a proposal and some patches posted. So what do we have to do on the Spark side for this? So first of all, we'll need to have a Spark fine-grained mode that emulates the Mesos fine-grained mode. I imagine that a lot of code can be reused there. And hand in hand with this are changes to support adjusting resources in the Spark Yarn application master. So then the big thing is memory. It's all nice that we can give back CPU and request it when we need it, but we're still forced to statically carve out a certain amount of memory when we request resources from the cluster. So the memory problem. We want to be able to have memory allocations preempted, and we want to be able to keep the application running. We want to be able to request a small amount of memory when we start up, and then request additional memory as we need it, let's say in an interactive session. So the big problem here is that usually RDDs are stored in JVM memory, and JVMs do not give back memory to the operating system. The only way to free that memory up for the operating system is to kill them. So what are some approaches that we could use to get past this? We could rewrite Spark entirely in C++. I'm sure a lot of people would love to do that. More realistic is to use some sort of off-heap cache. This was added in HBase but isn't very heavily used. The idea is that we would hold the RDDs in the executor processes still in the processes, but in off-heap byte buffers and access them from there. And those byte buffers can be freed and returned to the operating system. The second solution that I kind of like better is to forget about storing data in the Spark processes at all and push that onto Tachyon. An added advantage of this is that if a Spark process crashes because of bad code, the data is still there and we don't have to reload it from wherever we pushed it. And so Tachyon, for those who aren't familiar with it, is a service that allows you to store data in memory on a machine, and it makes it accessible to a variety of frameworks. It implements the Hadoop file system interface, so it's very easy to read in a lot of situations. And so this still punts the off-heap problem to Tachyon, but it seems like that's something that Tachyon is going to have to solve anyway. So that's long-lived Spark. How about having a single Spark application run work on behalf of multiple users? The issue with this is that applications are typically built to a single queue, and we'd want to build jobs to different queues. So we have our Spark application, and a few different people from different organizations in the larger organization want it to do things for them. One way of solving this is with the Spark fair scheduler. So Spark, I'm not entirely familiar with this, but the basic idea is that Spark has its own fair scheduler that runs inside of it, and within the resources that it's received from the larger framework, it can do fair sharing between different users and different organizations. So this is really two-level scheduling, and an issue with it is that it's difficult to dynamically share resources between Spark and other frameworks that want to run on the Hadoop cluster. So this is actually a problem that we've come up with for Impala, and the solution that we came up with at Cloudera is Llama, the low latency application master. Llama is basically an adapter between Yarn and Impala, and the central idea of it is that we run multiple AMs within a single process. So this allows us to receive requests in that process and then target them at the application master and hence like the queue that is most relevant to that query. So then we submit resource requests on behalf of the relevant AM, and the jobs are correctly billed to the Yarn queues that they belong in. So here's a silly diagram of what this looks like. Sylvia from finance's job comes in. We find out that she belongs in the finance queue. We direct the resource request to that queue, and then request from Spark from the application master. That's all I've got. Thank you.
Questions?
So quick question. When you're talking about sharing sessions, are you talking about sharing a JVM for multiple for multiple jobs? And if so, how you ensure that the class paths are not causing problems? Like several jobs loading log4j with different versions.
Right. So are you talking about in the multiple user case or in the long-lived case? Sharing a JVM for multiple jobs. That's a good question. I'm not sure.
Other questions?
I mean, there are class path isolation stuff that you can do there. We've done some of that in Hadoop to isolate the framework class path from the user class path, but that gets very tricky and ugly quickly.
Okay, any other questions? All right, let's thank Sandy again.